Everybody. So, in continuing with our cryptography section, I wanted to start by discussing symmetric and asymmetric algorithms. So, first of all, if we look at an encryption algorithm, this is a mathematical function or program that works with a specific key. And the strength and the key, based on how secret that is, determines its security. So when we think about a key, no different than a key, and it's structured with the individual peaks and valleys or notches in a key, those are equitable to the sequence of random bits that are generated from a range of allowable values. That range of allowable values is what's called the key space. The larger you make the key space, the more random sequence keys that can be created. And if you can generate more keys, then it's even more difficult to guess the key, as you might suggest or expect. So here, if we look at a key length of 3 bits, allows us to create 8 different random keys, 2 to the third power. And that key space, if we make that key space larger, then we would be able to have multiple keys in there that we could then rotate through. Okay. So just quick delineation between symmetric, asymmetric, and hashing. So in symmetric, that means that we're using the same key to encrypt and decrypt the data. In this instance, the sender and the receiver have to agree on the key before you transmit data. Okay, so typically this is to support confidentiality, but not necessarily authentication. Okay, it's also very fast, which is convenient, right? If we look at asymmetric, this uses 2 keys, one to encrypt the data and a different one to decrypt the data. This is used to support things like authentication, but also non-repudiation, which simply means that it's the assurance that someone cannot deny something, or knowing that somebody sent you that message, right? This is typically used in what's called public key cryptography, and we'll talk about that here in just a second. Hashing is used for verification, so we can use that to verify a password, perhaps, so we could store the hashed value of a password and verify based on that rather than one being stored in clear text. You also see hashing being used in, if you're going and downloading large files, you'll typically see a hash that's used for verification. What that does is it takes the length in terms of the size of the download and verifies that the sizes match appropriately using that. Usually it says MD5 hash or MD5 sum. So again, hashes are being used for password protection, data integrity checks, secret key cryptography, secure data storage, transmission, right? So symmetric cryptography, what we're talking about here is symmetric algorithms being used for encrypting things like hard drives. Public key cryptography, being able to securely exchange those keys, doing authentication, and then also digital signatures. So symmetric algorithms are quick. If you use a large enough key, it's pretty difficult to break. You only need one key again to encrypt and decrypt the data. So that makes it convenient for distribution, especially if you have several people you want to distribute that to. Unfortunately, it's difficult because you've got to manage all those different keys. And you have to be able to deliver those keys to the right people without it being stolen. Because once they have that key, then they can certainly get in, right? Types of symmetric algorithms are things like stream ciphers or block ciphers. We'll talk about some of those, and also the data encryption standard. It was originally developed, but have since developed a stronger standard called triple DES. And I've got a slide that kind of walks through exactly what that looks like here. So here is where we start to do things like substitution and permutation. So if we have a data block that is 64 bits in size, we would, triple DES will take that piece of data, it will split it into two 32-bit chunks. They will use substitution variables using the key. So think back to Caesar. We're going to do substitution on those 32 bits. Then we're going to essentially do the scramble, if you want to think about it, the permutation, and then we'll run through that multiple rounds. So in other words, in order to pull that back out, you've got to back all that stuff out with the right key in order to unscramble and then to redo the substitution to get back to your original data set, right? So splits the data. And it's being split mostly just so you can break the computational workload into smaller chunks so it can be managed better. Mangle the bits, right? Substitution, and combine the mangled bits and then perform that permutation operation. Triple DES will do it about 16 times. AES encryption, which works similarly, will do it someplace between 10 and 14 times. Another method is what's called cipher blockchaining. So this is similar to the way in which the blockchain actually works if you're thinking of cryptocurrencies, right? So here we take a single block of data, we apply block level encryption to it, apply that cipher to it, and then we chain the end of that onto, and it becomes the vector for encryption in block 2. So you have to have the previous blocks in order to recreate the entire message. And this is essentially how distributed ledgers are being used in cryptocurrencies, right? And instead of having one authority like you would with a banking system, in this case, all those ledgers get distributed, but each block in the ledger or each transaction in the ledger previous to is encrypted. And then it takes the verification that ledger to decrypt and understand the transactions behind it. So public key cryptography or asymmetric algorithms uses 2 different keys. So this is exactly what we're looking at in the lab exercise for this week, right? So we're using one for encryption. You distribute it widely. That's why it's called the public key. And then a different key for decryption. That's the one that's kept confidential. Clearly meant the private key, right? This uses 2 mathematically related keys, and the data encrypted with one key can only be decrypted with the other, right? Also called public key cryptography. The public key can clearly be known by the public. The private key is secret and only known by the owner. Used mostly for message authenticity and, again, non-repudiation, that you can't deny that you received the message, okay? So user A encrypts a message with the private key and sends it to user B. User B decrypts the message with user A's public key that gets distributed. RSA was a leader in developing this. This can also be seen in the use of TLS protocol being used in secure web navigation, and uses a one-way function to generate that key. It's also used in digital signatures. So you're starting to see more and more digital signatures being used for verification in applications like email and those types of things. So here's an example of Gloria sending a message. She's pulled that digital certificate to verify the authenticity of her email message. Paul has to decrypt that hash value in order to verify that message really came from Gloria. You also see digital signatures with SSL certificates. So it's not only encrypting the data between you and the website or the data that's being passed through that website, but it is also verifying the authenticity of, let's say, your bank or your credit union, or your credit card, or Amazon.com. Again, hash functions are taking the data and of an arbitrary length into some sort of fixed length on the output. And so you can use this to, again, verify data integrity. You can also do it to store a password. It's clearly used or often used in storing passwords inside database fields. So if you're storing user accounts like usernames and passwords, you don't want to have one that was being stored in clear text. Second of all, you don't want it to be obvious that one of them is 8 characters long and the other one is 16 characters long. So if you can all put them into a uniform 12 character long text, then it would clearly be more difficult to decipher because the number of values and or the number of characters in the hash might not be equal to the length of the actual password. Different hashing algorithms from MD2 to MD5 and then SHA-1 through SHA-3 are ones that are mostly in use today. As I mentioned earlier, MD5 is often used to verify uh, large downloads. Like if you went and downloaded a Linux distribution, there would probably be an MD5 with that also. You could verify that your download was not corrupted on the way down. So where is this in use? It's being used much more than it probably used to because we know that there are bad actors out there. We don't want our data being sniffed online. And so I think we're going to see more and more data services being secured without a doubt. And I think email is one of those in particular that's going to start to be used as well. In fact, there's a free email service out there called Proton VPN or Proton Mail, two different services. Proton Mail, especially, is actually end-to-end encryption for email, where you can sign up for an email account anonymously. So not only can you maintain anonymity, but you can also have your emails being encrypted end-to-end, especially for other individuals using the Proton Mail service. So I think you're going to start to see more and more of those email services become encrypted, more and more people using VPNs, not only to obfuscate their source IP, but also to make sure that their traffic is being encrypted, especially as we're on public Wi-Fi and those types of network connections. I had mentioned SSL certificates earlier. Those are becoming more and more required. In fact, Firefox now actually it gives you a warning if you're visiting a site that isn't SSL enabled or HTTPS. The way this works is browsers come with certificate authorities and intermediate certificates already pre-installed. So these are folks like your DigiCert or your GoDaddy or Network Solutions, Veritrust, and maybe some other ones as well. So those are all pre-installed. And if you as a web programmer go out and purchase one of those SSL certificates from one of those vendors or certificate authorities, then they're inherently trusted because we know them to be valid. You can still go and create your own digital certificate. In fact, you can create what's called a self-signed certificate. You can do it in the command line in Windows or Linux, and you can take that digital certificate and install it on your web server. And you can run your own web service with a free self-signed certificate. The problem is that web browsers are going to yak and give you this message and say, well, you've got an SSL cert, but it's not trusted because it's not pre-installed with the web browser. So if you know it to be valid, you can install the SSL certificate. And that can be common. A lot of system admins will that have admin control panels with some server utilities and those types of things. They'll do self-signed SSL certificates to make sure that their traffic's encrypted and the site's secure, but they're not going to go out and buy a certificate for $100 or $200 for every single one of their servers. The chances are they're the only ones accessing those sites, and so they don't need to go pay that money to have them pre-installed with all the browsers, right? This kind of gives you a nice walkthrough what that looks like. Is it uses the public key infrastructure in order to verify that, and looks up those CA or certificate authorities from those internal databases. And if it's not there, then it alerts the user. In our next section, I will start to discuss cryptography attacks, passive and active ones, and what effect those can have and how to protect against them.